Yes. Yes. Right now, it's like we had an episode about creation of the solar system. We know how Earth is created. Now let's talk about how it changed since the beginning.
So I'm just gonna guide you through the basics, the main events, or the ones I find interesting. So yes, this recording is very biased, just for your information at the start. I think we are first going to explain a bit about the how time works in geology, because there's many ways we talk about time and history that we first need to show. So you have time in time, just like we would explain time like this many years ago, that many years ago. And many of the whole Earth history is divided in certain time frames or certain patterns or certain like pieces that are grouped by that are usually ending in some natural disaster or another big event on Earth where it ends. And if we talk about time in time, we call it early, middle, late of this period. If we talk about it in rocks, so you can see time in rocks as well, we call it lower, middle, upper. So the terminology is a bit different between these two.
Why do we do that? Why do we say lower, middle, upper? Does it connect with the way like the rocks are found?
Yeah, so the general assumption is that you read time in rocks from low to high because sediment is put atop each other and every top layer of sediment is therefore newer than the bottom one, which is a very limited first view because obviously a lot of sediments have moved into mountains or uplifted or curled. Some are even upside down, but that's the basic of how it's basic principle of how it's formed and therefore how we call it, I would say. So this episode's going to be a quick glance through plate tectonics, climate, and large changes in flora and fauna.
Exciting.
Yes.
I'm
So
especially excited about natural disasters.
there's very little about natural disasters, to be honest.
No dramatic events like, eating popcorn. It's like, oh my god, what's gonna happen next?
I mean, there is, but those are the least interesting in my opinion. But I'm glad you're excited at the beginning. Then there's one thing I'm also obligated to tell you about, which is the golden pins geologists put in rocks to determine certain time jumps. So, for example, how do you say this? My English is getting worse by the day. If you go from one time period to another, there's usually something distinct that you can see in many layers of rocks in many places on Earth that defines this change. But there's always one location or one outcrop of rocks or one thing where it is defined. It's like a Oxford dictionary for rocks. Yeah, reference point. And they actually put a golden pin in this rock. They hammer it in. It's a whole ceremony. Yeah.
So you can visit these sites and see this golden pin.
Yeah. Cool. It's probably bronze though, or something less.
I don't think they put the gold there.
But they call it the golden pin, and there are these sites where they define these boundaries. We also have to mention the assumption or the scientific evidence that the Earth is 4.6 billion years old, and we count back to modern days.
How do we know that? From where did we get the evidence that the age of the Earth?
I think there are many ways to determine it. One of them by decay of certain elements, so radioactive decay.
Mm-hmm.
I don't think we're talking about billion years. It's not like on the year precise,
Yeah.
because it's so
Yeah.
long ago and we don't know much about this time.
Of
There's
course.
not much preserved as well. But yeah, I think it's mostly decay, right?
Yeah, it's mostly, I think, zircons, or at least this is what I know it, that we know the age of the Earth by dating zircons. I think this is really interesting science, that we can take zircons or minerals, and then by measuring how much uranium to lead you have there, you can determine the age. Let's maybe talk about it later when we maybe will be talking about how all the methods we use for dating. But yeah, it's a whole science within itself. So you see that it has, the listeners know that it's just not that simple, because everything overlaps with each other, and you can be Tika who loves sediment, but in the same time you have to deal with zircons, which are something I really like because they are in magmatic and metamorphic rocks.
Yeah, I think it's a very precise science. My interest lies more in the storytelling. So
Of course.
how and when and how precise it is, I believe it's cool. It's just not something my expertise has.
Yeah.
Lies. So the way we talk about this, billion years ago, million years ago, if you read in the articles, we say BA, so billion years ago, MA, million years ago, and then you count back to now. So now it's like 0 million years ago, because we are in the present. And we basically have 4 big divisions we describe. So it's the ancient time, the Precambrian. Then we have the Proterozoic. It depends on which order of magnitude you take. Then we have the Paleozoic. So it's old time, Mesozoic, middle time, Cenozoic, recent time. And recent is a very weird way of saying like 66 million years ago till now.
Or just, yesterday by the Earth standard.
Yeah, but if you think about it, like 4.6 billion years ago, like, let me emphasize the billion here.
Yeah.
66 million years ago doesn't sound
it's totally
too far away.
Not the
But
same magnitude, but it's still a lot of time.
Yeah.
If you think that humans live, let's say, I don't know, up to 100 something years, like that's it. And then like you have millions and billions. We are a speck in the universe of time.
Yeah. But for this episode, we're going to talk about the Precambrian or Proterozoic and then Paleozoic eras, because it's just too much to cover the more recent stuff. Also, I think it's more fun to talk to someone else about these times.
Mm-hmm.
So we'll arrange that later. So we're talking about the time from 4.6 billion years ago to 541 million years ago first, which is called the Precambrian. And you immediately see that it's like 4 billion years we're talking about. It's a large chunk of time, and it's the oldest chunk of time because there was very little to measure, because either everything is gone or eroded away or gone by magma, or we just don't see it at the surface. So we don't know much about it. But there's little things we know. If we talk about the first half of this chunk of time, so until 2.5 billion years ago, we talk about the Hadean and the Archean. And you hear by the name Hadean, Hades, hell.
Hell.
Yeah.
Hot.
It was warm and very inhospitable on Earth at that time. The formation of the Earth, as you talked about a little bit in your formation of the solar system as well, it was all very hot. It was all very volatile because of all the impact craters as well. So it was very warm, and the Earth was still cooling down into its layers, which it was busy with for the first 2.5 billion years of its existence. So it differentiated based on density. So we have the formation of layers, so we have the crust, the mantle, and then the core. There are still a lot of impact craters, impacts gone, which is like in this book they say the impact created the moon.
Or so
I think it's debatable, right? There's a lot of theory about this.
We will cover this more in the episode when I will be nerding out about my PhD. But generally, the giant impact hypothesis, let's say, largely is accepted for the lack of having a better explanation. But there are alternative theories. One of them would hypothesis, which one of them it's very interesting. Let's say there's for sure something smashing into the Earth.
From my understanding, something smashed in the Earth. Some other parts segregated, formed the moon, which has a big impact on how the Earth formed as well, because the moon creates all these tides and it has its own gravity pulling on the Earth.
Yes. definitely one of the very unique moons and satellites in the solar system, the Earth moon.
Yeah. And then we get the early formation of atmosphere. So before, the Earth was just open, bare to all radiation, therefore no life. Life was very hard to preserve because it was like radiated away almost instantly. But the formation of an atmosphere, of this blanket around the Earth, also made it more hospitable, both radiation-wise and temperature-wise, because you get the start of the greenhouse effect, the whole cushioning of the system from outer effects. So around this time, we already know and found the oldest fossil cells, which are about 3.5 billion years old, which is really old, especially if you consider that more complex life forms and actual visible interesting life, I would say, forms only after 500 million years.
But also like how fast, 4.6, the planet just forms. Then you have this period of cooling down. But boom, 3.5, we already have bacteria, right? So it's like, it's not a long time for the evolution or like the appearing of life to happen. It still was super, very hostile environment. And then there was still, there were already bacteria.
Yeah.
For me, it's amazing.
It's insane. It's insane. And so we find this oldest fossil, and there's many theories about how life formed on Earth. We still didn't figure it out completely.
Another episode.
There's too much.
That's because that's something that I also geek out a lot about the panspermia.
So in the book, they talk mostly about the theory that life formed around the volcanic middle ridges of the ocean, which is, I think, the least controversial and most accepted theory on how life formed.
Mm-hmm.
How that exactly works, complicated. We'll talk about it in another episode. And these cells were like single cell, nothing complicated, and it became more complicated around 2.1 billion years old when they started like ingesting each other and therefore using each other's abilities. And it sounds really gross, but yes, that really is how we think it happened. For example, you have a cell that can do photosynthesis, you have a cell that cannot. So the one that cannot do it ingests the one that can, and therefore has a new way of living or feeding itself.
New feature unlocked.
Yeah. It's literally like just grabbing something like Pac-Man and then evolving bigger and bigger. Yeah. As I said, very little of this era is preserved because of the plate tectonics being very little, the Earth being still very hot to actually have large plates on Earth, and very volatile, as I said. Then we enter the Proterozoic era, which is from 2.5 billion years ago to 541 million years ago. So we, again, take a large chunk of time.
Yeah.
But we get larger plates because the Earth is cooling, and they start congregating as well. So there are some supercontinents forming. Some names of these supercontinents are Nuna and Rodinia. And the Rodinia one you hear a lot in paleontology.
Also, you hear it. I would say if anyone remotely interested in Earth history, you would probably hear Rodinia before. I have one question. Is it already, because I'm a totally noob in this area. Of course, we went through those courses during university time, but I diverged into very different environment. Is it already, because you say you have a large plates and then you have supercontinents. This also already implies we got water, we got oceans, right?
Yeah. Oh, sorry. Oceans were always present. They were just quite hot in comparison to what we have today because of the active Earth.
Okay. The active volcanism and okay.
Yeah. There were oceans. There's a lot of water already. They were just warmer. Yeah,
because you said that the Earth, the origin of life is kind of water-based, right? Because you have the hydrothermal thermal vents. And they were, but for my understanding, they were more like ponds. But then you just create oceans. Is it correct?
Yeah. It's on Earth, it's usually either ground or water on the surface. So yeah, there would be very big oceans, but they would be a very different consistency. I think more silica-rich as well because of the mixture of all these chemicals into the ocean, not solidified yet on the crust. We'll talk about the contents of the ocean a little bit later. Let's see. We're starting at the Proterozoic, the pro-Earth, pre-modern times, I would say. we get larger plates because Earth is cooling, as I said. We have the supercontinents. Atmospheric oxygen is also rising in this period, so we have more free oxygen on Earth to breathe or to, well, in this case, make certain iron formations solidify. So we get the banded iron formations in this time, but then the oxygen raises too much along this period of time, and therefore it rusts away, basically. It oxidizes.
It's oxidized.
Yeah. So this is one of those important formations we found that led us to imply the oxygen content of the atmosphere, which we don't find today anymore. So it must have been very different from today. As I said, the life forms, I call them life forms because I cannot call them like animals or bacteria anymore. It's like a little mix. I don't know. It has a strict definition, but I won't define it that definitely. I think life forms fit a bit better. And they become more complex, but they are still very small. So you cannot see them with the naked eye, anything that lives, unless they clump together. So in this time period, we also get the Earth is actually cooled down. So we get the first glaciers on Earth from 1.5 billion years ago to 541 million years ago. And we find ice on very low latitudes, like around the equator is even evidence of ice, of this freezing and cooling structure of ice age. So somehow ice became, or freezing temperatures came very close to the equator, which causes all kinds of effects, right? Like we'll talk about this in a climate episode, but the snow reflects
the albedo.
The sun. Yeah, the albedo effect. So it reflects the sun, therefore it gets colder. There are all these feedback loops that make it colder. It is therefore
like a domino effect.
Yeah, exactly. This is its positive feedback loop that keeps making itself bigger. So there's this theory that there was snowball Earth around this time, so the Earth
froze itself.
Yeah.
Does it also correlates with I guess it's very early on in the development of also planet, maybe instability of the planet orbit, or is just purely because of the climate of the Earth?
Yeah, it's thought mostly the climate, yes. Because I think at 1 billion to 500 billion years ago, it was already pretty stable. The shape of Earth, the temperatures becoming more stable than before. Yeah, but it's one of those theories that is like, do we really believe it? There needs to be more research. There always needs to be more research. It's always the answer. But it's one of the most debated ones between scientists because they cannot agree if it really ever happened, how it happened, how we got out of it as well. Because somehow snowball Earth stopped existing, otherwise we would have snow everywhere today.
Yeah, exactly.
But it does tell us that it'll cool down enough for climate to take its grip on how the Earth is shaped. And the Precambrian or the Proterozoic, it's an interchangeable name, ends with an explosion of animal life. So we get these complex creatures looking like animals that are becoming bigger, more complex. And it is thought that this is due to the availability of oxygen in the atmosphere and the oceans.
So the more oxygen available, the more complex the life.
Yeah, we see it now as well for animal forms. That oxygen it's always a limiting factor because you need to breathe in order to burn energy.
It's pretty hard to exist without breathing.
Yeah, for plants it's the other way around. We need to pump CO2 in the air for plants.
For animals, it's like
yeah, we will poison ourselves. Anyway, we enter the Paleozoic era. And you can see we're making smaller steps in time now because there's so much more to tell in these steps. Because we know more, there's more evidence of different things. And so you'll see we'll start to make smaller steps. And we're going to talk about the Paleozoic, so the old time, which is from 551 million years ago to 252 million years ago. And it's seen as the start of more complex life on Earth. So we see mostly marine life exploding around this time, and mostly species without spine, so invertebrates.
I have a question, because like you said, mostly we see it complex life in a marine environment, but isn't it kind of biased by the record we have? Because of the plate tectonics, we don't have the record of continental record, let's say, and the marine life anyway tends to be preserved much better. Like you mentioned in the second episode, when we were talking about fossils, that the marine life is easier because the conditions of preservation are better.
Very true. Very true.
So
yes.
maybe there was a life outside, like I'm right now speculating, I have no idea.
Yeah.
That we just don't see it because we are limited by the factor of what we can find the archaeological, paleontological record.
Yeah, very true. I see where you're coming from. It is thought, though, that at this point there was not yet life on terrestrial, so on Earth above sea level, because the conditions there, even though we have this atmosphere and we have better climate, was still very harsh because there's no shelter from erosion because there are no roots or plants yet.
So there's no food.
Shelter. There's no food. There's no shelter. There's no water because the life forms we're talking about right now, we're not even close to amphibians yet. So they're all very dependent still on water for procreation, for survival, for shelter as well.
Yeah.
So I think we'll get there. We'll get the evolution of plants on Earth and then the animals following, basically, because there is opportunity created. But I think we're not there yet at this point in time. Yeah, it's still too hostile, I would say. So the Paleozoic is divided into a few subparts, and we'll talk about those one by one. And I think you're gonna recognize some of these names because these are the ones we use more often, and the Paleozoic is the first era we talk about more as well. So we started the Cambrian, which is 541 to 485 million years ago, and at this point in time, the sea level rises. And because of this ice that melts, right, after the snowball Earth, all this ice and snow melts, sea level rises, oceans go from aragonite to calcitic, which means it's just the component that is dissolved most in the Earth. And if it's dissolved more, if it's more present, these shell-making creatures are more easily preserved, right, because they don't dissolve, because this compound is more present. And why this is important is because calcite is way more resistant than aragonite. Aragonite is a bit more soft, so the shells we find today as well are mostly calcitic. We see also that animals start to radiate and become larger and more complex. And when I talk about radiate, I mean it's a scientific term for becoming more diverse, more abundant, more present, basically. So it's a radiation or an expansion of animals here. We see the first skeletons appear with a variety of teeth and tubes. So we get these hard parts, these calcitic parts in life, which give other advantages. And we see that this era is dominated by trilobites. And we already talked about this mug many times, but it's one I need to mention again. It's the mug from Paleotime NL, which my boyfriend is one of the organizers from, and says I'm a trilobit of a nerd. So if you ever get the chance to get this mug, please do, and think about the Cambrian, where trilobites were very abundant.
And these are, for the listeners, trilobites who don't know, these are the crickets, kind of like looking like cockroaches, right?
Yeah. They're called the cockroaches of ancient time. Yes.
Exactly. So you will see them very often in the pictures of Cambrian life when they just like crawl on the bottom of the ocean floor. You can buy them on like mineralogical exhibitions and stuff. They're quite popular there.
Yeah. And because of all the hard parts, because they have all exoskeleton, just like cockroaches, for example, they are more easily preserved.
Yeah.
As well. Yeah. In this era, you also find the first vertebrates, so spined creatures, or creatures with skeletons, and larger invertebrate predators, so without hard parts. And these are
softies.
Yeah, softies that actually start eating other softies. We end the Cambrian with a mass extinction of trilobites, which is a defining factor of this era. So we start with irradiation of life on Earth. We end it with a mass extinction, which happens often.
Can you tell me what is a mass extinction? Because that sounds like everyone died.
Yeah, it depends on how you look at it and what scale you pick. Of course, you'll see later in time we have mass extinctions only in the ocean. So a lot of ocean life dying because of factors impacting the ocean, becoming less oxygenated, for example. We have mass extinctions on Earth, and I think I would have to look up the definition. Yeah, I wasn't sure about the percentage. So it is defined as a rapid and widespread decrease in Earth biodiversity. So species dying out, many different. And it like decrease has to be 75% or more. So the extinction has to be 75% or more species lost
So
in less than 2 million years.
75% of biodiversity gone within how many years?
2 million years.
2 million years. That's very short time for geological scale, right?
Yeah.
So it has to be really rapid change in the environment. Do we know why the Cambrian mass extinction happened?
Probably a lack of oxygen in the ocean. So it is thought that oxygen declined rapidly, and there are many triggering factors for this, like tectonic shifts in the ocean, and therefore creating a lot of oxygen sinks, mountain building, ocean stratification because of climate change, and therefore no mixing of oxygen in the ocean. There are many explanations which it's hard to choose from, I would say.
So there are competitive theories, but there's no like one definitive answer why the decline of oxygen in the ocean caused the mass extinction.
No, and probably that they went hand in hand.
Hand in hand, okay, so like build-up effect.
Yeah, like the one causes the other as well, because if you have a very active volcano creating less oxygen in the ocean, it also changes the climate, which in case can have an effect on ocean currents, which can have an effect on stratification. So usually it's not just one thing.
Okay.
It works together as a complex system, Earth is, right?
Yeah, makes sense.
So we end the Cambrian with the mass extinction, and we enter the Ordovician, which is 485 million years ago to 443 million years ago. And we get to see more creatures like we know now. So we see some fish without jaws still. So the jawless fish, which
how
start
does
to
it
appear.
even look like?
Yeah. How does it even look like? We'll have to post this on social media.
Yeah, I'm just gonna look it up now.
Yeah. It looks weird. It's like your, I don't want to say this. It's like your grandma in fish form.
Oh my god.
Yeah.
Okay, it looks
like the teethless.
It
jawless.
looks hilarious. Like we really have to post it on socials, guys.
I think you have the hagfish or the lamprey in front of you, right?
I put Ordovician
the round one.
period. I put Ordovician period jawless fish, and it looks bizarre. It looks always surprised. It goes like.
Yeah, there are many types of fish. We have the hagfish as well.
I have like Arandaspis.
Yeah.
Yeah. So it just looks surprised.
Funky. Yeah. Yeah. So this is the jawless fish is a big group in the Ordovician. We also see coral reefs expand in the ocean, which creates a whole new environment for species to inhabit, right? This is also the first time where we find spores of earliest plants. Then the invertebrate fauna also starts to diversify, so the ones without the spine, like corals, all kinds of shell creatures, the echinoderms, so the urchins, yes, that's a word. We call them in Dutch sea hedgehogs.
Sea hedgehogs.
So I was trying to find this word, but it doesn't exist. It is not a thing in English. Urchins, sea urchins. It's not even close. But they look like hedgehogs, so to be fair, they have these.
They definitely do. But it's also, isn't it like the sea cucumbers? Are they also there?
No, the sea lilies.
Sea lilies.
Yeah. Crinoids. These shell type animals, like the similar to what we now see are mussels, for example.
Mm-hmm.
They eat a lot of plants or the plankton, the plant material in the ocean, which is what stromatolites are mostly made of. And stromatolites are these like spongy, wavy structures of plant material that were very common in ancient life or in ancient time. But because of the extensive grazing from these shell-like creatures and burrowing into the structures, stromatolites decline fast. We still see them today, I think, but not often. They're very rare. At the end of the Ordovician, we have 2 mass extinctions again. It's like a recurring theme on Earth. These mass extinctions, we usually define the biggest 6, not the biggest 5, and it is thought we are in the 6th one right now, but we'll talk about that later when we get there. But these are two like tiny mass extinctions. There's no way you can talk about a tiny mass extinction, but less recognized, right? First one of the warm-adapted species, and then the second one of the cold-adapted species. At the end of the Ordovician, we also find the first signs of continental glaciation, which is an interesting shift from only oceans freezing over to continents freezing.
Because you also mentioned about the glaciers on Earth, the ice, right? But that was the Proterozoic. So where was the glaciers?
Yes, it was sea ice mostly.
Sea ice. Okay, so it's okay. It's like icebergs.
Yeah, exactly. Or at least that's how we interpret it. It could also be that there was continental glaciation and we just don't find these continents anymore with the scrapes on them.
Okay.
We have to...
Limited record. You know?
Yeah. There's always a chance there were already continental glaciers, then we don't find them anymore. We enter the Silurian period.
I remember, because I was always forgetting about it.
It's the in-between, right?
It's just the name is so forgettable. And then when we had to have an exam, when we were going through all the geological time periods, I was like, what was after Ordovician, before Devonian?
Where is
Silurian.
Yeah, Silurian. So in this time period, it extends till 419 million years ago, 443 to 419. We see the shell-type structures, snails, ammonite kind of things like the nautiloids radiate again, and also trilobites. They have a whole new era. Yeah, they didn't die out. Okay, they just had a mass extinction.
Okay,
They didn't go extinct.
Yeah. My friend that we really need to get on this podcast, shout out to Alex Clark, he loves snails. So we can just make him talk about snails for the whole episode. So probably he right now hates me when I said oh yeah, I totally forgot about the Silurian era.
Important period for him, but yeah.
He's like, this is snail period.
There's just too much to talk about for it to be extensive about snails. But we'll talk to him about it all. So you can imagine after this glaciation period in the Ordovician, we now have rapid sea level rise because of the melt of all this happening. So the sea level rises again, which creates all new environments to get into. We also see the first land plants form, which is a very important evolutionary step, both for plants and their structures and for the opportunities and habitats on Earth that could be inhabited.
You're getting tired, I can see that.
I'm really trying. We can do this. Okay.
We can do this.
I wrote down a lot, so it's helpful. And these first plant species were like the horsetails we have now, so no vascular system to transfer water through the plant. They barely had any roots because you don't need many roots in the ocean. Like the seaweed just floats, right? Or it attaches to a rock. It doesn't have roots to pick up moisture or grow into soil, and it didn't have leaves yet.
Yeah, this is apparently I went to the one of the conferences I went. I usually pick one day when I go random sessions, and then I somehow ventured into the session of paleo people, I guess. Sorry if I offended anyone. And they were having this heated debate about leaves, and I was like, man, yeah, the leaves are super important because of these and then seeds and whatever. That was a whole different universe for me. I was amazed that it's still geology, but they were debating about timing of leaves and importance of seeds.
Yeah. I think it's paleontology, paleobiology, paleobotany, however you would call it, a mix of these things. Yeah. So they were very primitive species still, with no
not the paleontologists. Just the plants.
True. I have to. Good one. Then, following the first land plants, they formed enough shade and respite from the elements and less erosion, so critters could follow. So the arthropods, which is a very generic group of animals, and combine the scorpions, the spiders, and the insects.
The insects were bloody fast, and they're gonna be the bloody last.
Yeah, they're pests. Right? Even then.
It's just imagine those. I also heard that because of the oxygen that they could grow quite big. Is it true?
Yeah, we'll get there.
Okay.
Yeah, it's the Carboniferous. It's later in time. Okay. But they get huge. We have dragonflies of 2 meters wingspan.
Okay, disclaimer, I love smart books, so when you tell me wingspan, the only thing I hear in my head is like Akotar. And I'm making a promise to our listeners. I'm gonna be even more unhinged because I really want to make episode about geology of like Prithian.
Yeah.
Okay,
Same.
so no wingspan references, please, Tika, otherwise you're gonna get cancelled.
Okay, we'll get to the size of insects later, right? Insects, the size of insects. Still in Silurian. So we have these first land plants, we have these first critters on Earth, but plants do not get far into the continents yet because we still do not have these root systems, these vascular systems to travel, or water to travel from far away into the plant. So it's all still close to sea in wet environments. This time we also see the first births without eggs in animals, which is an interesting shift because the egg was one of the first basic things after cell division or
So what was
procreation.
first, the egg or the chicken?
Yeah, I would say egg.
I mean, the chickens came way later, so I guess it was egg.
Yeah. In paleo, if you ask paleo people, it's always egg.
Okay, good. Then we can always like market it as the episode. In this episode, you're gonna find out what was first, the egg or the chicken.
At the end of the Silurian, we have another sea level drop, and we see the first jawed fish. So the first ones with teeth as well. And they expand to freshwater habitats as well.
So right now what you're saying is that we have degradation between sweet water and salt water, right? And was it also created just because of we start having ice and then it was the reservoir for fresh water and then this is reservoir, the ocean is just generally reservoir of salt water.
Yeah. I didn't read specifically into that. I'm guessing that's the reason, yeah. Yeah, for ice to melt, rivers to form, lakes to form, or these estuary type situations, delta.
Yeah. Okay.
They could move from salt to freshwater habitats. The same for mollusks, so for shell-like creatures, mussels. We entered the Devonian period, which is 419 to 359 million years ago, and we see the first ammonoids, so the ammonite family.
Which I guess is also like a landmark of paleontology. I think if I think paleontology, I think like trilobites and ammonites,
Yeah, those are the ones that are most easily found, most widespread, easily preserved as well. So yeah, you see it a lot. If you go to south of England, you see them everywhere. It's really nice. They're very nice ones. They first were straight, like just tubes of shells, and they become curled later on. So the more curled, the newer it is, probably. Generally, it's very generally speaking. The jawed fishes start to radiate, and we have sharks now, which means there's a lot of predation from these jawed fishes, right? This is also the time we see the first fish with lungs, which creates a whole new
first fish
option.
With lungs, you mean like which could breathe air from the atmosphere? Okay, that's huge.
There's actually still a group living today, the lungfishes.
I want to see how they look like. Where is my mouse? I have too many screens.
Yeah, so it's actually, they still call it lungfish. They look just like fish, but they breathe a little bit differently than with the fish we know today.
And they are freshwater, apparently.
Yeah, so you can imagine this being a step towards like these life forms on land, because this gets closer to amphibians already.
Yeah. It kind of looks like, this... I know shit about fish also in English or in Polish, so both languages I'm dumb. But it looks like this fish which is like at the bottom of lakes, and then it also has this like fins, which kind of could look like hands and toes,
Yeah.
So it's slowly it's getting there. But they also look terrifying. I'm scared of fish, so if I would see it in the lake, I would be like, nope.
I always find them so alien-like. They look scary somehow.
They look scary. And also, I think fish are just scary because they don't blink, They don't blink, and
that's the thing.
That's the thing.
Yeah.
Creepy.
They're so squishy and soft, but not soft at the same time.
Yeah, no.
Fish is not my favorite thing.
No. Fish is, yum in the fish burger, but nah, in nature.
So we have these lungfishes starting to show up in the fossil record, the radiation of the jawed fishes and sharks. And then on land, we start to see more complex plant forms, such as trees and forests.
Wow.
Also,
So finally, the leaf people are like, yeah, Devonian.
Yeah, stuff's happening at the Devonian. It's actually depicted mostly for its forests in paleo art as well. And it has one advantage here because this is also the time where the first seeds start to evolve. So spores need a lot of water to transport and also grow into a plant. But the seed plants, they are a package of food that is transported with the plant, with the seed. So therefore, it has a lot of advantage on expanding into land and being less dependent on water.
And also, like, it probably can cover longer distances, right? Because if you can create spores, there's more opportunity for it to get, carried by the wind, carried with the river. It can, like, spread a bit more.
Yeah. Seeds have a huge advantage over spores in this time.
Sorry, seeds. That was me. Seeds, not the spores. Yeah.
We also see continents that start colliding with each other, causing orogenies, or the formation of mountains. We also see the first vertebrates on land, so the first spined creatures going into land because the trees provide shade for these types of animals, so the land becomes accessible to them. Because you can imagine like a very slimy, slimmery amphibian type animal going into full sun.
Yeah,
it would dry out.
It would dry out. KO. Game over.
So these trees provide shade, therefore opening up land for these types of animals as well. Because like insects don't have this problem; they have this outer skeleton that protects them.
Keeps the moisture inside.
Because of the evolution of the jawed fishes, we also see the evolution of ostracoderms in the Devonian, which is fish with an outer armor skeleton.
How does it even look like? You tell me so many weird shit that I always want to look up, and then I'm gonna have nightmares.
Yeah, it's like cockroach fishes.
These ones, okay, yeah. They look like frying pan, but swimming.
Yeah, so they develop armor to protect themselves. I mean, I'm saying this wrong because evolution has no like direction. So they do not evolve to protect themselves. It's just the ones that have this armor survive more, procreate more, therefore proliferate. But you get the gist of what I'm saying. Yeah. I guess we'll do these misconceptions later.
When we talk about evolution.
Just know I understand how evolution works. I'm just wording myself a bit weird.
You're simplifying things.
At the end of the Devonian, we have the proper amphibians. So first we had these critters going onto land, but these are proper amphibians that can shift between water and land, and further collision of continents causing more mountains to form, and the climate becomes colder because of the forests. The trees form roots, so the soil is more broken up, and therefore we have a little bit more weathering in this time period. Also because the forest CO2 is taken out of the atmosphere, therefore decreasing the greenhouse effect and Earth becoming cooler, basically. We still find a lot of salt-like deposits in this area because it's still dry on Earth. Forest starts to form which contains moisture as well, but they're not widespread yet. So we still see a lot of dry areas with these deposits. 2 more to go.
Can
you handle it?
Yes.
Okay, good. We get to the Carboniferous, which has a very interesting name because it's what you see is what you get. A lot of carbon. So it's 359 to 299 million years ago. We see a lot of climate change, a lot of coal formations. Coal swamps form because of the increase of plant mass. So we have these forests that break down and these swamps start to form. An interesting change is that the seas change to aragonitic seas again. Therefore, shells becoming
less
different.
Preserved.
Yeah, less preserved, softer as well. And continents start drifting closer and closer together, which means that reefs become more abundant because we have many more warm inland shallow seas. As the oceans start to become smaller in between the continents because the continents move together, it also gets more shallow. And more shallow is warmer because there's more sunshine in there, which causes carbon deposition of the reef structures that live there. Amphibians start to radiate on Earth because of a lack of competition and predation, because they're still the only ones there big enough. The first ones there as well. And at the end of the Carboniferous, reptiles start to be present there as well. So the move from amphibians that are semi-aquatic still to reptiles becoming fully terrestrial. And the giant insects, as you said, swarm the Earth because of the high concentration of atmospheric oxygen, and they could be bigger.
More
because
oxygen, we get bigger.
Yeah, because oxygen in insects is limited to atmospheric concentration because they don't have a blood system, same as we do. So the amphibians were still dependent on water for reproduction. We see the same with spores if we compare it to plants, but they still need water for their eggs and their offspring. In the meantime, reptiles started creating amniotic eggs, which made the shift from semi-aquatic to terrestrial possible, so they could move farther into Earth. We also see the evolution of gymnosperms.
Oh my god, again, funny word. I'm gonna Google it and see how it looks like.
I was gonna explain.
Sorry.
So a gymnosperm, it basically means a naked seed. So a seed without a... You're a visual thinker, I see.
Oh man, I'm such a child sometimes. But yeah.
But we all know a naked seeded tree. It's a Christmas tree, for example. These pine cones are the naked seeds where these seeds actually come out. Later we see the covered seeds, and then you would talk about an apple, for example.
Yeah.
So they have pine cone-like structures, and they become widespread in the Permian, so in this time period. Widespread in the Permian, which is the next period we're talking about. In the mid-Carboniferous, we have a large spread of ice caps, also close to the equator again. And we know this because of the layers of rock from that era, from that location, had cracks because of a freezing-thawing cycle. So they make very specific structures in the rock.
You can also see it nowadays.
So the continents are drier because of the ice caps, because of the climate changing, less weathering, therefore more atmospheric CO2 present, which ends the ice age again. Classic feedback loop.
So in the right, you said that you have the coal and the swamps and a lot of oxygen and like this very rich flora, and then you start creating ice caps, so you went through small ice age.
Yeah.
Is it happening at the same time, or is it happening one after another?
Yeah, it's in sequence. Yeah.
Okay, in a sequence. Okay.
Yeah. So we end with the dry continent, less weathering, more atmosphere, end of the ice age. And that's also the end. Yeah, and that's also the end of the Carboniferous.
Mm-hmm.
So we start the Permian with the end of an ice age. Basically, that's the definition of the change. The Permian is from 299 to 252 million years ago.
So really small.
Yeah, only a little bit less than 50 million years. But it's an important era, especially because of its end. But it's also the last period we talk about in this episode. And it contains a further development of and spread of these naked seeded trees, so the gymnosperms. And we see the evolution of more complex vertebrates. So jaws and teeth evolve differently depending on the food source it fits. And we see that instead of swallowing prey whole, it's also possible to use these teeth on different food sources.
It's funny because when I hear gymnosperms, I see this like cone being a gym bro.
We need to let AI make this image. It's good for social media.
For social media.
Ever seen gymnosperms?
Where's my protein bar?
Sounds gay.
Oh my god, yes. We do that.
Yeah. So they develop more, they spread more on Earth in the Permian period, in the last period of the Paleozoic. In the late Permian, deep seas become more stagnant and depleted of oxygen because it's super warm. And when it's warm, we see that now on Earth as well, the ocean starts moving slower. Therefore, no oxygen mixes. The deep sea pump doesn't work anymore, which we will talk about in an ocean circulation episode later. And the climate is warming and drying because of the formation of the supercontinent we all know quite well, I would say, which is Pangaea. It's the one our current continent system is
made from.
Yeah, made from. Is that a good word?
Developed
Created
from. Yeah.
It's Pangaea that cracked apart and now forms Northern Africa, Southern Africa, the Americas, Europe, everything. But in the Permian, it all came together from some other continents and formed a supercontinent. Because of the large area, it became super dry. And because of this large landmass, no oceans, sea levels drop.
Yeah.
We see a big difference between the air temperature between the equator and the poles. So we have a large contrast from equator to poles. And because of this dry period, we see a lot of salt depositions from this era. And the funny thing is, most salt we consume today is actually formed in the Permian. And I find it extremely funny when you have these like jars of
Expiration
salt
date.
with an expiration date of tomorrow. Like it's 250 million years old. How is it
it can
gonna expire
survive
tomorrow?
one more month.
Yeah. Like a month on like million year scale. Yeah, but it expires. Yeah, sure. It's a mineral, cannot expire. But okay. In this period of time, we also see the first land mammals, but they're still very scarce, and they start to, well, also roam on Earth. And in the late Permian, we have the first therapsids, which are warm-blooded animals. So before we had the reptiles and amphibians, they were all cold-blooded animals. But here we see the first warm-blooded animals. And there's whole science on how to see if they're warm-blooded or cold-blooded. I actually learned something about it using synchrotron data again. So I'm mentioning it again, I'm sorry.
Synchrotron!
But it has to do with bone density and structures, and it's been a while since I dove into it, but very interesting research as well to see from only bones if it's warm-blooded or not.
Crazy.
In the middle of the Permian, we have a mass extinction in most of the oceans, but at the end of the Permian, we have the largest mass extinction of all time. From the top of my head, 98 or 99% of species died out. Yeah.
Largest extinction of all time. All time. Sorry, that was my impression of Kanye West.
Nice. Yeah. So at this point, many species went extinct, many species of corals, and it's called the end of an era, basically the end of the era of ancient life, the Paleozoic. And I think that's where we're ending the episode today because it's already been way too long. We arrived at 252 million years ago, which you would say we have very little left, but there's so much more. Yeah,
I think the closer we are getting to the modern time, the more we have of a record and the more complex the life becomes, because we saw that it developed from like Pac-Man swallowing cells to get different functions to literally start having land mammals and warm-blooded animals.
Yeah, exactly.
Which is crazy. I mean,
it's crazy.
When you think about it, how long I think it's not even fathomable for human brain to understand this time chunks. Because how much humans changed over, civilizations-wise, technology-wise, over 2,000 years, 6,000 years, 8,000 years. And that's just thousands, and we are talking millions and billions.
It's a whole different scale to think on, which is the hardest thing to learn as aspiring geologist or paleontologist, to see how these timescales interact and how you can
I think there's also this part of cynicism. Like some geologists I find very cynical because they're like, climate change, life on Earth, been there since forever, it's gonna be there forever, climate change, it was already back then, different circulation of oxygen level and acidity of the ocean. And I was like, but that's why we died! Like mass extinctions,
This is why we have these things.
I understand, dude, that, we as a life on Earth, we preserve, but I would like to preserve the human life, Only because cockroaches are gonna survive doesn't mean that humans will survive. And sure, I appreciate your knowledge about geological timescale, but it doesn't mean that humans operate on geological timescale. We are babies.
We are very much alive now and not millions of years.
We are newborns. We just barely crawl out of the timescale.
Yeah. Anatomically modern humans are only 55,000 years old.
Yeah. So for the scale of being on the Earth, we literally mean nothing to what was before and what it's gonna be in the future. So maybe, your ego should die down a little and focus on
generally
surviving.
A good idea to dial down your ego.
Yeah.
Yeah. So I hope you enjoyed this walkthrough.
I did. Time. It gives you a totally different perspective, which I think it's very important. I like to, when I think about geological timescales, past life, also about formation of planets and all the timescales, it just literally makes you feel very small, very it puts you in perspective. And I think certain type of people in the planet, I'm not gonna name names, should think about it and should think about what you want from life, because why are you a billionaire? Why you're hoarding this trillions and trillions of millions? For what?
Yeah. You're so insignificant.
You're
impactful at the same time. It's difficult.
It's like, like in couple of 100 years, it's not even like million years, it's all gonna be gone. And like maybe you should think about impacting the current situation for everyone rather than hoarding whatever you have. My take.
Definitely. I think this is where we're going to end it. The next era we're going to talk about is the dinosaur era, and we're going to get an expert on that because it's way more interesting than listening to me ramble about something that is not my expertise, even though a lot of people are interested in dinosaurs.
We gonna get for you guys, for you, my beloved listeners, we are gonna get you a dinosaur nerd.
Yeah. But yeah, in due time.
In due time. Stay with us.
For now, this is it.
Stay with us, stay alive, don't mass extinct, and do better. Do better.
Always do better.
Always do better.